Lecture number 7. Today we are going to see pressure on two sides of a liquid surface. Pressure on two sides of a liquid surface. Suppose we consider liquid surface, then we consider two types of liquid surface. Suppose this is the convex liquid surface. Suppose this is the concave liquid surface, and third one we consider plane liquid surface. Now here we consider when surface is plane, then resultant force of tension cancels and pressure on it is 0. Here pressure is equal to 0. When surface is concave surface, then resultant force of tension is in upward direction. That means here you see. Suppose we draw this tension forces, surface tension force like this. Then resultant of these two is in the upward direction. Now due to action reaction, we consider the force due to atmosphere is in the downward direction. That means when the surface is concave, then pressure on upper surface is larger than pressure on lower. Now we consider, suppose third one, suppose surface is convex surface, then suppose we show this forces of the surface tension in this direction, then resultant is in the direction. Resultant force of surface tension is in this direction, therefore force here we consider in upward direction due to action reaction, and therefore pressure is small. Here pressure is small. Here pressure is large, and here pressure is 0. This is all about pressure on two sides of a liquid surface. I hope you all understand this. Now we consider next article here. Explanation of formation of drops and bubbles. Explanation of formation of drops and bubbles. Liquid drops and bubbles are spherical in shape, you know. A bubble or drop does not collapse because the resultant of the external pressure and the force of surface tension is smaller than the pressure inside a bubble or inside a liquid drop. Now we consider here, suppose we consider this is the drop like this. Suppose this is the drop which is spherical in shape, whose radius is, we consider, suppose r is the radius. Here Pi, this is the pressure inside the drop, and we consider Po, this is the pressure outside the drop. Now here drop is spherical in shape, then excess pressure we write here, excess pressure is, we write here, Pi minus Po. Now suppose we have to increase the radius of this drop from r to delta r. Suppose I consider here, suppose this is the new drop whose radius is r plus delta r. That means you can see here this much amount, this is the delta r. Delta r is increase in radius. We have increased the radius from r to r plus delta r, where delta r is small, so that the pressure inside the drop remains almost constant. Now here we consider, suppose A1 is surface area of the drop, initial surface area of the drop. We can write here A1 is equal to 4 pi r square. This is initial surface area. Suppose this is equation number 1. Now suppose A2 is the final surface area. We can write here 4 pi into bracket r plus delta r bracket square, and this is the final surface area. Suppose this is equation number 2. Now here this equation 2 we write here like this, that is 4 pi into bracket, we expand this r square plus 2r delta r plus delta r square. Therefore we write A2 is equal to 4 pi r square plus multiply this 8 pi r delta r plus 4 pi delta r square, and suppose this is equation number 3. As delta r is small, therefore delta r square is also small and we can neglect it, and therefore we write simply A2 is equal to 4 pi r square plus 8 pi r delta r. Suppose this is equation number 4, because we neglect this term. As delta r is small, delta r square is neglected because it is very small. And the increase in area, suppose I will write dA is the increase in area is equal to A2 minus A1. A2 minus A1. We subtract equation number 1 from equation 2. This 4 pi r square gets cancelled and we get only 8 pi r delta r. Suppose we write this equation as equation number 5. This is increase in surface area. And therefore work done in increasing this surface area dA is stored as excess of surface energy, and therefore I will write here dW is equal to T into dA, or we write T and dA means this much, 8 pi r delta r. This is dW. And suppose this is equation number 6. Suppose F is the force causing the increase in area dA, then that small work done dW in terms of force we can write here F into delta r, because force into displacement, delta r is the displacement. Suppose this equation number 7. And excess force F, we know F is equal to pressure into surface area. Therefore I will write here Pi minus Po into 4 pi r square. Pi minus Po into 4 pi r square, because force is equal to pressure into area. Suppose the equation number 8. Now we equate, that is or we put the force value of force from equation 8 in equation 7, and therefore we get here dW is equal to we write here Pi minus Po into 4 pi r square into this delta r as it is. Suppose the equation number 9. Now from equations 6 and 9, here you see this equation and this equation. If we equate these two from equation 6 and 9, we can write here T. We write T into 8 pi r delta r, right hand side of the equation 6, is equal to, I will write here Pi minus Po into 4 pi r square delta r. We equate equations 6 and equation 9, and therefore is here. Suppose we cancel different terms here. Suppose this 8 and 4, I will write here, suppose this 4 and this 8, this cancels here, here we get 2. Then pi cancels completely. Then 1r here, 1r. Also delta r cancels completely. And we can write here, suppose 2t is equal to, I will write here, that is pi minus po into only r. And therefore pi minus po, this is the excess pressure, is equal to, I will write 2t upon small r. Suppose this equation number 10. Now this is the excess pressure for drop. Now if we consider bubble, for bubble there are two surfaces, inside and outside, and therefore if we come write, or if we derive this total derivation for bubble, then here you see, here we have taken, that is dA is equal to 8 pi r delta r, and we multiply this equation by 2, and if we finally calculate all these, then for bubble the excess pressure pi minus po, this pi minus po comes out to be 4t upon r. Suppose this is equation 11. This is all about explanation of formation of drops and bubbles, or excess pressure inside the drop and bubble. These two formulas, that is pi minus po equal to 2t upon r and pi minus po equal to 4t upon r. For drop, this is for drop and this is for bubble. They are very much important. When you are going to solve the examples, then you can get, or you have to use these two equations. This is all about that is excess pressure or explanation of formation of drops and bubbles. Okay, now we will see next article, capillary action. Capillary action. First we will see what is meant by capillary. Capillary. A tube having very small diameter is called as capillary. Now when a tube having very small diameter is dipped into the liquid, this capillary is dipped into the liquid, then we consider here the liquid which partially weights, wholly weights, or does not weight. Then depending on these, here we consider in this capillary there is liquid level rises, falls, and this rise or fall of a liquid inside the capillary is called as capillarity. Capillarity. This is the property. That means rise or fall of the liquid inside the capillary. We call it as a capillarity. Now, this is all about capillary action and capillarity. Now, in next lecture, we have to explain how this capillary action takes place. Thank you. We will see in next lecture.